Okay, section 6.2, quantum theory. Now we're going to talk about a different type of approach to thinking about electromagnetic waves. So back in section 1, we talked about electromagnetic waves, right, as oscillating disturbances with a wavelength, which we use lambda to represent, and frequency, which we use nu to represent. And then we talk about the speed of the vibration as it moves in some direction. Okay? So that's one view of electromagnetic radiation or electromagnetic waves. Okay? There's another interpretation which is called quantization. And essentially the idea here is the following, that Max Planck figured out that if you take a container, you paint the inside of it black, you coat the surface some black material that's really absorbent of light, and then you heat it up, what you'll find is that there are electromagnetic waves bouncing around in there inside. Okay? And the frequency of those electromagnetic waves depends on the temperature. Okay, so the hotter the temperature, the higher the temperature, the higher the frequency of the waves that are taking place in there. So Planck, what he did was he tried to calculate the energy distribution and the frequency distribution of what's called a black body. And the radiation that's inside there is called black body radiation. And what he found was that he could match up his theory with that of observation, with experiments, by making the following assumption: that there was a quantized amount of energy, meaning there's a certain amount of energy which is proportional to the frequency. And so in order to make it an equality, what he did was he multiplied the frequency by this constant of proportionality, which is now called Planck's constant. He didn't call that himself. He wasn't. But we now call it Planck's constant. And what that says is that essentially you can think of the radiation that's produced in here as being caused by vibrations. And those vibrations have a certain frequency. And the energy of those vibrations is given by this equation right here. E is equal to h nu. Okay? The energy of a quantum of energy, which is the smallest amount of energy that you can have, one quantum of energy, is proportional to the frequency, and becomes again an equality when we have this constant. The value of h is now accepted as somewhere around 626 times 10 to the negative 34 joules times seconds. And this constant pops up all over atomic interpretations of matter and energy. Okay. So you will see some slightly varied values given. You may see 6.63 in your textbook times 10 to the minus 34. So again, pay attention to which value of the constant that you're using. So the idea essentially is this: that imagine that you wanted to calculate the potential energy of a mass on a staircase. And so you have this mass which is sitting here at the bottom step. And the mass can only exist on these individual steps. So the question is, what's the energy difference of moving the mass from the lowest step up to the first step? So we'll call that E. That's the amount of energy difference between these two states here, state 1 and state 2. Okay? And so what we're claiming is that inside this black body radiator, the smallest amount of energy that a wave can contain is given by this particular equation here. Okay, it's very powerful for various things. And in your textbook, it'll talk a little bit about things like laser pointers, how those are related to this issue. Okay, now another interesting experiment. This was really theory right here, but it was based on experimental data. But a different type of experiment is an interesting phenomenon called the photoelectric effect. And the photoelectric effect is, in a sense, the basis for things like the cameras that are built into your cell phones now, or a digital camera. The photoelectric effect. The photoelectric effect is based on this following experiment. Imagine that we have a metal conductor. Now, we all know that metals conduct electricity very well. So one way to think about that, one way to approach it, would be to say that metals just have these electrons, which are so loosely held by the nuclei that they're essentially free to roam throughout the different atoms. So an electron might be on one atom in one moment, but then on a different atom the next. So it's often described as a sea of electrons. They're just able to move all throughout the different atoms. So here's a little depiction of that. So there's the piece of metal with these free to move around electrons. And the photoelectric effect is based on a couple of experiments. So one thing that was measured was the idea, what happens if you try to shine radiation or electromagnetic waves onto the surface of this metal? And so imagine that we use red light. Okay? And the idea would be that, okay, if we shine red light on the surface, what happens? Well, essentially nothing happens. The red light bounces off of the surface and nothing happens. But suppose instead we use ultraviolet radiation. So I'm going to depict the ultraviolet waves as having a shorter frequency. I'm sorry, a shorter wavelength. Okay, and these are going to be ultraviolet. UV, we call that, right? So red light is in the visible range with a longer wavelength, and ultraviolet waves are in the UV, so they have shorter wavelengths. Okay? Now, essentially what happens is, if you use the same brightness or the same intensity of light for these two different sources, when the red light strikes the surface, the light just bounces off and nothing happens. But the ultraviolet, what happens is the radiation is absorbed by the surface, so the energy goes into the surface, and then an electron is kicked off the surface, and that's called a photoelectron. So that's a photoelectron. It's an electron that has been emitted or ejected, it's photoejected, by the absorption of energy in that ultraviolet radiation, in the wave that's striking the surface. So then you start saying, okay, well, so one thing we would say about this is that the energy of the red light is dependent on its frequency, the frequency of red light, which is around 10 to the 14th hertz, around 5 times 10 to the 14th hertz. The energy of the ultraviolet radiation would be equal to h times the frequency of the ultraviolet radiation. And the ultraviolet radiation has a larger frequency, a higher frequency, I should say. than the red light. Lower frequency. So this is our explanation so far as to why the ultraviolet radiation is capable of ejecting an electron off the surface of the metal, but the red light is not, is that essentially because ultraviolet radiation has a higher frequency than red light, it has more energy. So that higher energy is enough energy to eject the electron off of the surface. In fact, we can write it as an equation, which is exactly what Einstein did. And Einstein wrote it this way, which is the energy of the photon, h nu, would be equal to the kinetic energy of the electron, so I'll write electron under here, that gets ejected, plus something he called the work function. And the work function is essentially an energy holding the electron to the surface of the metal. So what happens is the more energy that goes into the atom or into the metal, if electrons are ejected, the more energy that goes in, the faster they'll move when they're ejected out. They'll have more kinetic energy. Okay? So what has to happen is, in order for the electron to be ejected, the photon, remember that's this term here, this is the energy of the photon. So this is of the radiation. The energy of that radiation, these waves coming in, that energy is equal to the amount of kinetic energy that the electron has after it's ejected, plus the amount of energy that was holding it down onto the surface. So this energy right here has to be larger than this one in order for this one to be above zero, right? So like if this is the energy holding it down and this is the energy that's going into it to knock it off, this energy has to be greater than that one in order to knock it off. And if it's much greater, so if the energy of the light is much greater than the energy of the binding, the work function, then the electron, when it's ejected, will have a lot of kinetic energy. Okay? So energy comes in, the energy comes out in the form of motion of the electron, but that difference in energy is essentially the energy that's holding the electron down. Okay? So then you try this next experiment, which is you say, okay, well, suppose I do this. Suppose we say, okay, well, red light has a certain amount of energy that's dependent on its frequency, but what if we use more light? What if we make the light more intense? So we're just going to use more waves. Okay? We should have more energy, and maybe we can get to a point where there's enough energy that we can eject the electron with the red light. And it turns out it doesn't work. It turns out that even if you double or triple or quadruple the amount of red light, the electrons still don't get ejected. They're still stuck to the surface. So then you say, okay, well, let's do the same thing with the ultraviolet light. Let's use ultraviolet light, but let's use more waves. Let's put more in. More energy, right? And what you find is you get more electrons. The more UV light you put in, the more electrons get ejected. So not just one, but two or three or four. So this leads us to the idea of quantization of light. The idea is that light is comprised of little particles, which we call photons. And so the reason that the red light is not ejecting the electron, we're not getting a photoelectron, is that when one of these photons strikes the surface of the metal, it doesn't have enough energy to knock the electron off. On the other hand, ultraviolet radiation has a photon that has enough energy so that when that photon is absorbed by the surface, it essentially ejects the electron. It's a one-to-one relationship. Every time one of these particles, which we call a photon, strikes the surface, you get one electron ejected. The one-to-one relationship. And so the photoelectric effect is an important phenomenon, not for just purely for its technological reasons, that our technology is based on it. Much of our technology today is based on it. But it's also this idea that the explanation for the photoelectric effect is that light is actually comprised of these particles called photons, which do have a wavelength and do have a frequency. So they are still waves, but they are also particles. And so these particles strike the surface, and if the particle has enough energy, it can knock one electron off of the surface. This is actually the explanation that gained Albert Einstein the Nobel Prize in Physics. Okay?